Hi, welcome to the channel that uploads every single day without fail. This is a milling machine. I don't know a lot about milling machines. I have a metal 3D printer in there that does most of my heavy lifting. I know that this bit spins and this table moves forward and back, and that's about it at this point in time. But I bought this one, and I thought I'd bring you guys along for the journey of kind of putting it back together and getting some of the grind cleaned off of it, because we have a race car to build, and we have a few parts like this and maybe something down there that it would be really nice to make out of aluminum, and to kind of do some testing between the metal 3D printer and a admittedly 25-year-old CNC machine. Step one is cleaning. French door treatment. Yeah, I did change the wall in the shop. Thanks for asking. Before I even clean or anything, I'm going to level. Obviously, I'm going to get a precision level, but this is like even roughly, let's get it close. Oh, I have lights in here, don't I? All right, I'm going to spend the next while vacuuming a lot of vacuuming. Oh, I'm going to take doors off too. These are the moments when I'm editing when it's really embarrassing that there's like 15 minutes of me trying to take doors off here. But first, a word from our sponsor. Hi, it's me, I'm the sponsor. This is my metal 3D printer. If you need metal 3D printing, there's a link in the description below, or go to wk-printing.com. There's a ton of room to work back here. So the astute of you may notice that this is a 3-phase machine, and this is single phase coming into the box, and that's because I have single phase, I do not have 3-phase, but that's okay because these old fit-all machines should run on single phase with a little bit of a spindle power hit, which I'm not too worried about because I like aluminum, and if I cut Inconel, we'll reevaluate the situation. Hang on there, I found a really good way of showcasing this completely by accident. This is a 50 millionth style test indicator, and I own it because I can't read Facebook Marketplace listings, and I thought it was 5/10. This is a 1939 Atlas 10D lathe. It hits tolerances of hopes and prayers, and the style test indicator is way too fine for it, being that this chuck has a run out of about 2 thou. My original intent with all of this was to show how even a 50-degree change in temperature can alter the outside diameter of a part that you're milling, especially when you're trying to hit these level of tolerances, which is kind of superfluous on this mill anyways. But what I found with the back gears engaged is if we bring this onto the part and come down to where we're actually about roughly zeroed out, and I turn it by hand, you can see that my surface finish is actually pretty good, but every single time I touch it with my hand, she jumps a little bit. That's because there's wear in the chuck, there's wear in the bearings, there's wear in all of the pulleys. Like, everything's just a little bit old on this, and it just wasn't designed to hit these kinds of numbers. But an interesting thing occurs with the back gears engaged. When I kick the lathe on and bring this in, she jumps around like crazy. And that really puzzled me for a little bit because it wasn't my surface finish. When I spun it by hand, it worked just fine. And I put the slow motion camera, my phone, set on 240 frames per second, and sure enough, every single little change in that needle on that super fine, way too fine dial test indicator is 4 frames apart at 240 frames per second. So it had to have been the vibration in the motor or the torque difference in the motor in between those waves as it was going down, because this is a single phase plugged into 110 electric motor. So I'm going to get this hooked up And unless you're a building inspector or anything to do with the state of Arizona, then I'm going to hire a professional electrician to come in and set this up. So obviously we're going to do that first. All I'm doing today is, and according to the internet, the source of all true knowledge, is driving the VFD with single phase 220, which is the biggest thing that I'm questioning. And then the factory transformer is basically... I'm sure that transition was perfect, especially now that I have a cold. What we actually did is I ran two 220 lines to the Baldor drive, and it works perfect on single phase. I just made a jumper. Instead of using the transformer as a step down, what I did is I pulled one hot leg of my 220, ran a common or a neutral, and used that to drive the amp drive and the computer and everything like that. The run's on 110 single phase anyways. It's all run through the disconnect box currently, and I also ran an air line out here. And if the government asks, it's on an extension cord, which it kind of is. This is SO cord. So yeah, that's what's going on back here. Everything seems to be happy, and yeah. This is a CRT. It works by throwing electrons at a screen. This is an LCD. It kind of works in that same way. It's a different flavor of electrons. This one works perfectly fine. It's getting a little bit dim. It's getting really, really burned in. I thought in the interest of me seeing things clearly, it would be fun to replace it with this American-made nice LCD panel that should, according to the internet, plug and play right in, and everything bolts up nicely. So we will see how that goes. I'm going to very, very carefully get this out of this container, because if it doesn't work, I'd like to put it back in. But we'll see. That couldn't have fit better if I tried. This should be 110, and I think it'll work, but I just want to double check it with the wall wart before I go and mess with this any. Much better. Hey, that actually looks pretty good. Nice. So let's talk about the metal 3D printing. It's a lot easier setup-wise than the mill, because the part is programmed automatically. All I have to do is set down a piece of paper on there. It takes a day and a half to print, but I can go and do other things. I don't have to sit there and babysit it like the mill. From there, it goes into a wash station, which washes out all the wax, because this still shows up in a spool, but there's metal powder bound in a wax that allows it to be extruded into the actual machine and to actually form a part. And then this is the sinter. So what it does is it takes a part in its what they call a green state after the wax has been washed out and cooks it down in the center, literally shrinks the part almost 30% and binds all of that metal powder together to create a really, really strong part, like those parts you saw were out of 17.4 stainless steel. This is, at the end of the day, a hot metal tube filled with argon. However, it is ultra high purity argon. It is a fairly expertly controlled metal tube, pressure and temperature-wise. One of the benefits in Metal 3D printer outside of the time spent is to create parts that just couldn't be manufactured or any other way. This is one of the suspension wishbones that I paused halfway through because I changed the design halfway through, that was going to be out of 17.4. Because of the inside geometries and the inside is actually fairly hollow, it has a triangular frill pattern, this is able to be quite a bit lighter and quite a bit stronger than any part that I can machine out of billet. This is an impeller for a pump that's kind of in the works that I might still finish someday. But neither of these parts could be manufactured on the mill, especially not cost effectively. The biggest downside is size limitation, specifically with the sintering machine. I'm limited to a part that's about 3 inches by 3 inches by 12 inches at the end of the day, which makes me able to do stuff like the suspension wishbone, but larger parts like the control arm and the shock holder and everything gets a little bit more difficult. So with my newfound ability to cut metal, I ran into an issue with the portaband, which is a tool I use a lot because I don't have a regular bandsaw. Well, I bought a bandsaw. In traditional Wesley fashion, I didn't buy one that actually worked or was nice or in any way was actually what I needed today to cut metal. I bought one that is more of a project and will end up probably costing more money than if I just bought a nice one. But it has the benefits of being absolutely ancient. Before we even loosen anything, I think you guys can see the crack that is formed there, which is fun. There's probably a crack underneath here because the wheel isn't tracking correctly. And completely on the other side, there's also this one. So all of these are going to be very, very fun. That is slowly going down. The valve is closed and it's slowly going down. Outside of like a lot of rust, this blade isn't terrible. Might keep it as a spare. So the bearing itself actually looks pretty good. This looks slightly less good. I looked in here and saw that both of this was rubbing on both this and this because I think somebody put this too far on the shaft. So I'm going to back it out just a little bit so that that's not rubbing anymore. Much better. I think it's a really good sign that I went to unplug the connector that has a spider and it just completely like came apart. So that's a good sign. Take two. Woo! Okay, that's something. I cannot overstate how much the lights dim in here when I turn this on, but that was it on the motor. I saw sparks. That's tripping a 20 amp breaker. I'm probably thinking that motor's not happy. But also, if I take tension off of it, this sounds fine. Like this sounds pretty good. It's not great, you know. The lead screw on this is kind of interesting because originally I thought it was broken because you can spin it this way all day long, but as soon as you turn it this way, it actually engages after a little bit and tightens up, which is pretty cool because I think what that means is when you loosen this, like releases from the ball screw and you can just pull it out and like set it to wherever you need. And then when you actually want to tighten it down, it goes in. So obviously I'm going to pull it all apart, but that was just kind of a neat little thing. Hopefully it still works after I clean it. Yeah. So we're going to go with the principle that all of the oil hopefully leaked out of the bottom and I can just put fresh stuff in. It actually doesn't look too bad in there. Why did that go in the wrong way? Oh, that's better. Much better. Cool. So I really wanted my first project on the mill to be something easy and out of aluminum. I bought some 1/2-inch plate, and we're going to drill a couple of holes, mill a hole in the center, mill the groove down the middle like that, and hopefully I have feeds and speeds right. That would be nice. That would be cool. So I'm using Fusion 360 to program all of these, and I'm not going to go through do a CAM tutorial or anything because there are plenty out there. Go to Titans of CNC. There's a lot of good results out there for CAM programming. I am using the Fadal post processor that somebody on the forums posted for Fusion 360, and so far it's been working really, really well. Again, I'm kind of new at this, and I'm sure there are a bunch of people in the comments that will show me what I'm doing wrong and that there's a million different ways to do this exact same thing. All of these came with the machine, but this is a tool offset block that's 2 inches and has a little dial on it. I like it a lot. It's a lot cheaper than obviously a probe or anything like that. And for this system, once it goes into the rhythm, once you actually start your tool setting cycle, it moves very quickly. I do a warm-up program on the spindle, just set it at 1000 RPM for a couple of minutes just to get everything flowing in the spindle. And then this has a CalMotion module that sits in the box that allows me to send programs over with an SD card instead of having to deal with the serial port. This is a 1998 machine, so it actually has, I believe, 512K of memory. Cool. Yeah, compared to the old one, I think that's an improvement. So, man, I hope I got the holes lined up. I actually didn't check if this fit before sending it, but it looks like it probably might. Idle back on that side. Cool. Yeah, this isn't bad at all. It's genuinely pretty straight and pretty square. It's not bad. I could probably dial it in a little bit more. I need to get coolant set up. That's a priority. And the feed cylinder is going to happen sooner than later because this is in the hold position right now. And yeah, that's not hold. So yeah, we're going to deal with that sooner than later. But other than that, she does pretty good.
Come on, perform better, climb higher, educate away. I am all my degrees, my masters. Hey, look at me, I am somebody. It's what I've learned at
I got some really bad chatter on my facing pass over here. That's because my feeds were way too slow or fast or something. We're going to have to play around with that. This over here is nice. I went quite a bit faster over here on my spindle speed, so I think I was just way, way, way too slow in here. It also might be because I'm like 1/4 inch plate in here. I don't know. Anyways, the biggest thing that I'm learning that's really, really difficult on this is fixturing. So I kind of built this little coaster, and I have these holes here. This jaw is already fairly beat up anyways, so I'm going to drill into here and like hard mount onto the soft jaws over here. This in here is beautiful. I'm happy with that. It's just surface finish got a little bit rough there, but so I lied. I thought about it, instead of me like refixturing everything over there on that vise, it would be a lot easier for me to just run the beginning of that program again on a second. I need longer screws. Hang on. Anyways, instead of me setting it up in a different fixture and then like drilling and trying to align all of that, I can just run the first part of that fixture, bolt this, since these are standard threads, bolt these to this, and then everything remains aligned, and it should be pretty good. Man, I hope those are really going to clear on my end mill. They should. They might. I need to set my height. So theoretically, because I milled this in here, I can move up exactly 1/4 of an inch, because that's the thickness of this plate, without re-measuring my tools. Alright, last shot with this old Tony Hams, I promise. I reset my tool offset to match our new fixtures, or actually how they're ordered now, and then I just added 1/4 inch to our fixture offset from when it was set in there. Well, that ain't it. If I had to guess, I'd say we have an origin wrong. Heights are great. Outside of a very nice cut right through where it's not supposed to be, and a little bit of a surface finish issue, I believe that was exactly what we're looking for. Outside of one almost indistinguishable flaw, this is actually a part that I'm really, really happy with. The feeling on the bottom of these is almost flawless, and I could probably have done my finish pass with a little bit of a bigger end mill going through there, but the chamfers and the edges look pretty good, and once I got my speeds figured out by adjusting it on the machine here, this did pretty well. I just needed to not slow it down over here. And looking at the edges over here, that's not bad at all. I'm pretty happy with how that turned out, and the chamfers look good. I stepped those chamfers down to avoid the bolt holes, and I think that actually helped quite a bit compared to the inside there where I got a little bit of chatter out there on the tip. For a part that I refixtured, I mean, that's not bad at all. So I'm on the side that I think I got a pretty good finish on, and wow. Okay. This is supposed to be 0.22, and it is. There we go. I didn't quite expect that to nail that on the first time, so I found a low spot. I'm sure my fixturing was off a little bit over here. And of course, this isn't faced on the back, so who knows on that. But yeah, I'm pretty happy with that. Also did this little piece on the flat stock, and once I got the speed up on that face mill, it seemed to be a lot happier, although my chamfer was a mile off. That's not going to be perfect. I'm 3/4 of a thou over. That's not bad. Alright, I think that's going to do it for this time around. I'm really happy with how these aluminum pieces turned out, considering that I've never cut anything on aluminum on a CNC mill before. I'm really happy with how the bandsaw turned out, and the plate did even better than the aluminum. It's weird how the steel went even better, but go figure on that one. I know that 9 months between videos is not great, and the YouTube algorithm would love that I would upload every single day if I absolutely could. I can't. I just don't have that kind of production schedule. What I'm really shooting for is one good video a month, 20 to 30 minutes long, and I'm really excited for the one that's coming up on the race car. That's going to be a great video, so get subscribed for that. And yeah, if you would like, subscribe, comment below. Thank you very much for watching.